like
And that'd
6
be
in the morning.
still on Fridays.
From 6 in the morning to like 8?
Yeah, I could maybe post it. I could post it either the night before, like at midnight, or something like that. It's a possibility.
Usually at that time, I'm driving up to the U to get to just
Oh,
a certain building. So after this class, I can just go to my next one.
Okay. Okay, well, let me think a little bit more carefully about that. This next quiz is going to be much.
I have a question for quiz 1.
Yes.
I am just looking at the quiz solutions,
Yes.
just like how it was solved, and I'm noticing on question 5,
Yes.
I put the same number that the solution is saying, and then the quiz is saying I was wrong.
Yeah. We're going back with. I noticed that there's a couple of different problems, and I'm not sure how those calculations went wrong. But the original calculations for the answer is actually something like 54, but I think the numbers got changed going into it. So that one is that you will be getting. I think people were getting credit for if they get to the one that was, I think, 62. We went back and we changed all those scores, so then if that's what you picked, then that's the you get extra point on it. So we have changed that. We've identified.
Oh, mine wasn't changed, and I put the 62.
Yeah, me too.
Okay,
Yeah,
we'll make
me
sure.
as well.
Yeah, I'll make sure that that's being done.
Okay.
Yeah, in fact, there's a TA online. Maybe they could make that change. But we did decide to do that because there was that confusion on that one. That's correct.
That was question 5, right?
That was problem 5. Yes.
Yeah. Okay. Thank you, Professor.
Sure. Okay. So, anything that people want to bring up, other than all the questions on the quiz and homework and all of that's coming out okay?
Yeah, I actually have a question. Did you mean to grade the homework the way that you did?
Did I mean to grade?
I don't want to you to change my score, but you gave me 40 out of 20 points.
Yeah, the point totals in Canvas are wrong. On Gradescope, it says it's graded out of 40, but on Canvas, it's graded out of 20.
I mean, I think you should leave it out of 20 personally, but.
Well, it all just works out. I mean, we end up whatever that, and I think what I did when I put it onto Canvas, I put 5 points per problem, but the TAs I think assigned 10 points per problem, and that's the difference. So I'll get that straightened out, and it doesn't matter because what we'll do is that we add up so if we stick 10 point per problem, 5 point per problem, we just need to be consistent. So if you're getting 10 points, that's the way that it's going to be, and so I'll keep that through the rest of the semester. And then we just add up all of your homework scores, divide that by the total amount that is possible, and then that gives you a percentage. So the percentage isn't going to change whether it's 5 points per problem or 10 points per problem. We just need to be consistent. So they all have the same weight. Okay? But I'll check. I'll make sure that gets worked out with the graduates or the TAs. Excuse me? Okay, well let's talk about the material that I want to get started on today, and that is material on the find the little plug-in thing here so I can have a little bit better audio. Okay, I suppose you can still hear me. Yes?
Yep.
Okay. So I'm going to go to share screen.
Can you guys hear me?
Yes. Okay. So let's bring up this. Okay. I would assume people can see this. Yes?
Yeah.
Okay. Wait, something doesn't seem quite right here. Just one moment. Go back to the beginning. Okay, yeah, that slide was out of place. But let me go back and look at that slide. That'll get rearranged on the final edited version. So today I want to talk about the properties of fluids. And I keep talking about this thing called PVT, pressure, volume, and temperature. And so this idea that we have two independent thermodynamic states allow us to completely define the state of that fluid. And then by knowing that state of the fluid, then we can calculate the other accompanying properties, for instance, internal energy, enthalpy, entropy, the whole thing. So, but we need to be able to have a place of identifying the state. And the easiest way for us to be doing that is to understand it from the standpoint of pressure and volume and temperature. Why? Because we can measure those directly. I can measure pressure, I can measure temperature, and I can measure the volume of a particular liquid. So that's really the basis of everything that we're doing in thermodynamics is these PVT. And then from there, we then define these other properties like internal energy, enthalpy, entropy. So let's think about phase change. Now, phase change, we're pretty familiar with this, and this is a picture here that is a picture of what you would expect to see for water. And it helps us to identify the different states. One state here is on a PV diagram, excuse me, a TV diagram. Okay, so here's specific volume and here's temperature. And so when I have a liquid, I'm looking at a pretty small specific volume. Remember the specific volume is the inverse of the density, right? So if I have a high density, then I have a small specific volume. The small specific volume, that puts you in the liquid. And so the liquid is at a pressure and a temperature less than its boiling point. And we call that the compressed liquid. So if I look at the water that comes out of my tap, that water is maybe 50 degrees Fahrenheit, 1 atmosphere pressure. 1 atmosphere pressure, that puts me, it compresses it compared to where it would normally vaporize, and it would vaporize at room temperature, maybe 10 kilopascals. But now I'm pressurizing that, and so it's compressing it if it can get compressed. Now, we don't really talk about compressibility of liquids much. But in general, that region is what we call the compressed liquid. On the other side, we end up with this superheated vapor. And we can think of superheated vapor as maybe we boil that water, and then once we have that steam, then I heat it up even farther. Okay, so when we get into, say, thermodynamic states of water vapor in air, that's typically defined as superheated vapor. If I have steam that is going into a high pressure turbine that has been heated up past its boiling point, then that's going to be superheated vapor. So this is a condition where we think of getting to the boiling point of the vapor, and then I just add more heat to it to push it more and more into the ideal gas regime. So this really does look like ideal gas out here. It'll behave like an ideal gas, and it's liquid back in here. Now, in between 0.2 and 0.4, I'm undergoing a phase change. So I get up to 100 degrees C, and now my water starts to boil. And as I'm going across the boiling curve, across to here, I'm going from 100% liquid to this point here, where it's 100% vapor. And those states are pretty interesting. In between, there are some interesting unstable states, and that would come from the Van der Waals equation. The Van der Waals equation would define something that would look like this for the overall state. It would look like, and then that, okay? And it's kind of interesting. It's because of the form of that equation. And this kind of is defined as what's called the spinodal. That's the maximum amount of superheat of the liquid that you could ever get. And the same thing, the maximum amount of a subcooled vapor. And those are really interesting states. They're unstable typically. This one here, you might run into this from time to time. You're coming up a compressed liquid and you heat it, and instead of vaporizing, it just stays as a liquid. And you can do that in a microwave oven. If you have really a clean glass, no nucleation sites. You put in really clean water. There's no place for those bubbles to form. And the result is it can go up into this regime here. And if something triggers it, it'll go unstable. And as a result of that, you end up with this. It looked like an explosion. Somebody just sent me a Canvas message and make sure I get this. Excuse me. Okay, so I'll answer that later. Okay, so if we put really clean water in a microwave oven and it's in really clean glass, you can get to the point where it goes superheated, and once it's triggered, then that energy that is associated with the superheat all goes into creating a vapor bubble, and those vapor bubbles then explode and blows that scalding water on top of you, so be careful. So when we think about what's happening in these different processes, I thought I'd put together a couple of videos that would show this.
A electric tea kettle, and turn this
And
on because it's kind of an interesting.
this is
demonstration of
supposedly, why don't I have
phase
sound on
change
it?
process. And I thought I'd
This
do
is a
that
little
for
pot
you.
where I'm
Couple of things that you're going to be
boiling,
putting
heating some water, and it's nice because it's got
that
these little
sound
LED
is actually those little bubbles that come up.
lights on it, so
They
that
come
you
up and
can
they
see
collapse.
the bottom of this
So
a little
the
bit more
collapse
clearly.
of those bubbles
And so this is the first part.
have
This is where I'm
acoustic
heating up
emission.
that
And so
compressed
what you're hearing
liquid
is the
up to
collapse
the
of the
boiling
bubbles.
point. And in a
And
regular
you'll also
coffee
see
pot,
those
what you're
bubbles that
seeing
are
is
being
that
formed at the
just the
bottom,
bubbles that
place
are
where
showing
the
up
heat is
down
being
here on the
added in.
bottom.
You can see those little
And
bubbles going up and then disappearing. Those
so
bubbles are collapsing
they
into
come up
bubbles.
and they come up and they
You're
collapse.
seeing that
Now,
essentially
if we
those
have
bubbles are
sound
coming
on
out
this,
because there's a little
what we
bit
would
of
hear
air
is
that
a
comes up.
kind of a
There's a little bit of
crackling
air
sound.
that is sitting
And you
in
hear that
between
when you
the
put a
temperature that
pot
surface
on
is.
the water, you
Once
hear
the
that kind of a
temperature of the
crackling sound
metal
as it's
starts to
first
grow,
starting to
then
heat up.
it releases
That's
these
the sound of
chemicals
those
and
bubbles
collapses
coming
it.
up
That's
and
the
collapsing. You can
release sound.
see, yes.
We can
And
kind
you're
of
also
hear it. It's
seeing a
just
lot of
quiet.
natural convection.
Oh, okay.
Can't quite see
Don't
some
know
of
if
those
there's a way I
convection
could turn
spots,
up that volume.
but basically
All
what's
right. Anyway,
happening
you
is
can hear it a little bit. That's
hot
great.
temperature on the bottom, basically the boiling point. These
So
bubbles are coming up
as you
and
listen to this, that has
they're
a
giving up their energy
particular sound,
to
and
the
it's
cooler
because of these
liquid
bubbles that are over
phase.
here. They're coming up. Those things are coming up and collapsing, and they put off an acoustic sound. So that's the first thing you hear as you're listening to or watching water boil. And then the second thing that you would watch would be a little bit later on into the process.
Skip ahead a couple of minutes. We'll get a little bit farther on into the boiling process. And what you're seeing now is a much more rapid
Yeah,
vaporization.
wait a minute,
You
can I
see those
stop
bubbles
this?
that are coming up. Those bubbles are
Okay,
essentially
and now you're
beginning to the surface.
later part. Now you're
Kind of
seeing those
hanging around
bubbles
the
are
top.
coming exactly from the
You
heating
also
elements.
notice that the
Before
sound
it's probably a
changes.
different nucleation site. Now these
Instead of
bubbles
having that
are making it all the way to the
really crackly,
surface.
much
If you can
lower
hear this, it's
frequencies,
a
that means
much
that the
lower
bubbles are
tone,
bigger
and
creating
that's
pressure
because
at
the
the
bubbles
surface.
are bigger, so it gives
The
off
measurement
less
when they
surface
collapse,
energy, so it
find
gives
out
off
that those
less
bubbles are making
energy
it
and
all the way
collapse.
to the
And
surface.
once you
That
get to
means
the
that
point of
higher
full boiling, and now we're
at the
completely
saturated
saturated throughout,
temperature,
all of that
above the
water
boiling
above
point,
is at the
bubbles
saturation
are coming up.
temperature.
Now
So
with that
now we're
steam
at
that is
that
coming out of the
saturated
top
liquid
of the
point.
tea kettle,
Any heat that I
this is
add
an
in
automatic
just goes
shut off,
into
so it's
making
gonna know
more,
that
changing the phase
temperature
from
has
a liquid
gotten
state
close.
to a vapor state. And this thing will turn off
And then
once the hits the
settle
temperature. Once the surface temperature down here reaches a particular point, automatic control is to turn it off. So that's what happens when we're changing phase, and we're seeing that coming up to this point here. Then we're going through this process, the boiling to this point here, and then the vapors that are coming off the top of that pot are really coming out and then being into this regime here. Now, this is the function of pressure, right? If I'm at the top of a mountain and my pressure is less, then the temperature here, where that phase change is going to occur, is going to be at a lower temperature than if I go to a higher pressure and that phase change goes to a higher temperature. And if I go to really, really high temperature, I get to the critical point. Critical point is like 300 and something degrees C. And every fluid is going to have a critical point. So this kind of a behavior is common to all different fluids. And so part of what we need to understand is, given a particular pieces of information, where are we? Are we here? 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 I mean, what is that state? And how do we define it? Because once we identify the state, then we can identify its thermodynamic properties.
Professor, can I ask a quick question?
Sure.
So one time I did put a mug of water into the microwave to heat it up, and then I took it out, nothing happened, and then I went to put in just a flavor. As soon as I put the first scoop, it exploded. It wasn't very large, but would that be that kind of thing that you were talking about?
Exactly. Whatever that is, that gave the nucleation sites within the fluid, and the higher the degree of superheat, the smaller that little bit of that bubble has to be able to have the thing explode. So what happens here is that you create a little bubble, comes up, you create a little bubble, and that bubble has a decision whether it's going to grow or collapse back in. And it has to get to a particular size before it will grow. And if it doesn't get to a particular size, it just collapses back. And so those tiny bubbles that are collapsing, that's what you're hearing, that high frequency. But those bigger bubbles, that once you get to closer and closer to the actual boiling point, then those bubbles are much bigger and then they collapse. But now you take it to the superheat, and what it's looking for is a nucleation site. The same thing as getting like the pollution that comes out of the sky at night. That what you're doing is it's those little pollution particles are crystallizing the ice. Those are the nucleation sites for the ice, and they do the same thing to make rain. They put little itty bitty particles up in the atmosphere under the right conditions, and those little particles create nucleation sites for the condensation of the water in the atmosphere. So you need a nucleation site. You need a place for it to get started. And in the bottom of the pan is typically just little imperfections in that surface that creates a little bubble that is sitting there. But if it's not for those imperfections, like if you have really clean glass, you're superheated. If you put in any kind of a contaminant or nucleation site, bam, that's going to go to a vapor. So that's exactly what happened. Okay, good point. Anybody else had a? Okay. So when we talk about PVT diagrams, these are a kind of two general surfaces. You can think of them as a three-dimensional surface, right? We have three independent variables, so we should be able to describe PVT relationships on a three-dimensional diagram. And so if I look at it on 2 dimensions, and in 2 dimensions where I'm just looking at what we would typically think of as, pressure and temperature, the two easiest things for us to be measuring. And we identify that for all fluids, we have this point here. That point is a triple point. And for a pressure less than the triple point, we're in a vapor, i.e. that's a superheated vapor regime. If I am at a temperature above the triple point and it's liquid, then I'm up here on this line, okay? And so at a particular pressure, I can be out here as a liquid, or I can be out here at a much higher temperature as a vapor. Okay, so these are essentially my vaporization line. This is going from a solid to a vapor, right? So that's called sublimation. Sublimation is interesting process that sometimes has a lot of value. One way sublimation is kind of interesting. Freeze-dried ice cream is an example of that, right? We're taking the liquid out of the ice cream, but we're leaving the material kind of intact, and basically we're just vaporizing ice crystals within the internal part of that. And this is what we're typically used to, this curve here, this vaporization curve. So we're going from the triple point, and we're adding temperature, and we go to higher pressure, so we get to higher temperature for higher pressure till we get to the critical point. Now, these are two interesting curves. These are a curve that goes from a liquid to a solid. And so essentially going from here to here, I'm melting, right? Or from solid to a liquid, I'm freezing. Well, it ends up that fluids have one of two different characteristics. They either have a characteristic that looks like this or like this. Now, this one is interesting, where you're going to this process here, because what happens is that as I get to the triple point, that as I go through freezing, that actually expands. And we see that with ice, right? That ice expanding is what breaks up pipes if we freeze them, right? Ice is expanding is why we see ice sitting on the surface of the water, why we see iceberg, because it is less dense than the water that is around. And if it melts, it goes right back to the same volume as the water that is around it. So the fact that it is less dense than the liquid phase is unusual. And if water did not have that property, we would have a whole different world. Could you imagine if the ice that froze on the top of a pond ended up just going to the bottom, and all that ice just kept going to the bottom? You would end up with a frozen pond, completely frozen pond. It's the ice that actually gives you some insulation and keeps that circulation from happening, having all the ice at the bottom. Also, what's interesting is the densest point for water is for water at 4 degrees. Not at 0, but at 4 degrees. It goes through a density minimum, and then the density starts, a density maximum at 4 degrees, and then the density decreases as I heat the water, or the density decreases as I freeze the water. So 4 degrees is the density maximum. The other interesting thing about this, if you had a fluid like this, then you would not be able to ice skate on it. Why would I say that you wouldn't be able to ice skate on it? Well, what are we doing with ice skating? We're on liquid. We're right here on this point where I've got a ice, right, a solid, and then I put it under pressure, right? Here's my pressure, so I increase the pressure up to here. And all of a sudden, I hit the pressure that is the melting point of that ice. So under the skate, if the temperature of the ice is high enough, under the skate, I have a thin film of water that is produced because of the high pressure of that skate blade on the ice. So that's why it becomes frictionless. You're not skating on ice, you're skating on water as a result of this melting process. That's why it's so slippery. Cold ice is not very slippery. Ice that gets pretty close to the triple point starts to get very slippery. You put a little pressure on it and it melts it, and it has that lubricating layer of water. So when I look at these the different kinds of fluids, this is the kind of fluid here that shows up in figure 324. And again, it is a three-dimensional surface. And I could be looking at it from the side that I'm seeing this figure up here, which is looking at it from this angle. So if I looked at it from this angle, I would see my vapor, my phase change line here. I would see up to the triple point, I would see my curve up here. Up to the critical point, I would see this, which is this piece here. And what's not shown is this change in volume going from here back to ice that sits behind that curve. Okay, that change in the specific volume. Other fluids will look like this. I get that change in volume. I go across along the triple line, and I get the freezing, and that solid is going to be denser than the liquid. And so I see this little change that keeps showing up versus the opposite here. And the slope of it is opposite. Now, something like Freon or that kind of material, it will be, like a R134A. It will look like that, and this will look like water. Okay, almost all fluids will look like this. Ammonia, R134A, all the new refrigerants all have that behavior. But water has got this little quirk here that makes it really interesting and really fun to ski on it. Actually, skiing is a little bit different process. I'll mention that quickly. If you're skiing in powder, what's interesting is that you're not skiing on snow. You're actually skiing on the air that is trying to get out as you're crushing that snow. So powder skiing is really, you're literally floating on the air pressure under your ski as it's trying to get out from the crushed snow. Okay. So, oops, we've already jumped over that. So we've got a couple of different other things that we need to be talking about. And actually, let me go back here and do something. I'm going to get rid of these. I'm going to put something else here. And I want to talk about essentially, the property tables and how do we get into these different values. Okay, so let me just mention here. Property tables. That's where we're going to get this information. And we go back, we think about maybe this T versus V diagram. And you have this vapor dome that looks like this. And out here is superheat. And down here is compressed liquid. And I heat this up and I go through this phase change. Now, as I mentioned, we need two independent thermodynamic properties to be able to define this. So if I give you a property that puts you right here, high temperature and pressure, so, oh, that's superheated. I'm going to go to the superheated vapor tables. Or I'm out here and say, oh, that's definitely compressed liquid. I'm way away from this dome. I'm going to be using the compressed liquid tables. What if I end up here? Now I've got a little bit of a problem. Are temperature and pressure independent on that line? And the answer is no, because that's under the dome. That is where I'm changing phase. I'm going from a complete liquid to a complete vapor, but I'm halfway in between or partway in between. So we need to define something else about that state. We can't use temperature and pressure to define it because they are not independent, right? Temperature is dependent on pressure, pressure dependent on temperature if you have a two-phase system. So you have to add in one other variable. And the variable that we need to specify is what we call quality. And quality is essentially related to some distance between those 2 points. So quality, I'll say X, is equal to the mass of the vapor divided by total mass. Okay? So I can write my value of X, the quality, as being whatever that average value of the specific volume minus specific volume of liquid divided by the difference between these two. So the difference between this is what I call the change of the specific volume going from a fluid to a gas phase. I don't rather see liquid to a gas, but the nomenclature is fluid to a gas phase. And so depending on where I am along this line, if I'm at this point here, then if I take this value, subtract off this, then divide by that total distance, that gives me the mass fraction to be that is specified here. Okay, it's a mass fraction of the total amount. So this allows us then to go to the tables, and if we have this information here, and this information here, and that information here, I could calculate the quality. Again, it's just the mass fraction of the vapor compared to the liquid. So if I say a quality of 100%, I'm saying that I have 100% vapor. If I'm saying a quality of 0, I'm saying a saturated liquid. I'm talking about being right there on that line. And if I have a quality of 50%, it puts me right there on that line. Okay, and you could also look at this average value. That average value is equal to 1 minus X times the specific volume of the liquid or plus X times the specific volume of the gas. Or we could be writing that as the specific volume of the fluid plus X, the change in the specific volume. Okay, it's a different relationships, but it all just is a leveraging rule to be able to find out what our value of X might be based on the mass fraction. Okay, and make sure I identify that this is the fluid and this specific volume of the gas. And this might be the average. Okay. So we could do that for any other property, since we're putting in energy per unit mass or entropy per unit mass. Then we're going to be using the same leveraging, the same mass fraction to be calculating all those other properties as well. So let's look at internal energy. First thing is that internal energy needs to be defined as a datum. And so here's the datum for everything. The internal energy for the fluid is equal to 0 at the triple point. And that defines pretty much everything. And my value of U, my value of U, F, is just equal to the overall internal energy divided by the mass, right? So it's an intensive property. And we could also define my value of U as being equal to an integral from 0 to t, 0 being where my value of U is 0, which is probably t at the triple point, of what we call specific volume. That could be, or a specific heat at constant volume. That could be a function of temperature. And then I integrate with respect to temperature. If CV is constant, then I'd say, well, U is equal to C sub V times T, or maybe more precisely, a delta T. That's relative to datum. Okay, datum being that point here. And I could also define my value of U as being equal to a change in U with respect, go back, C sub V, change in U with respect to temperature, right? And that's actually a definition of them. And if I wanted to look at what's happening under the vapor dome, U would be equal to, say, average is equal to U sub F plus X U sub FG. So if X is 1, then I am taking the internal energy of the fluid plus the change in internal energy and going from a fluid to a gas, and 100% of that if I've gone all the way. So then that would end up being X equals 1. That would give me the internal energy of saturated vapor. So, yes, question.
Somebody put in the chat, what is C?
What is V? Oh, C sub V. This implies change at constant volume. Okay, so we make that statement because I could also have a change in enthalpy, which is not happening at a constant volume. So we have these two different specific heats we need to talk about. For liquids, it doesn't make any difference. Specific heat, constant volume, constant pressure, it doesn't make any difference because liquids basically are incompressible and they don't really change in density much with temperature. So C sub P and C sub V doesn't really make much of a difference in a liquid. It does in a gas, and I'll show you why. We're talking enthalpy now, which is an H, and H is equal to U plus PV, okay? Pressure and specific volume. And to get an idea of the units on this, U has units of kilojoules per kilogram. And PV, if I put in P in terms of kPa and V in terms of meters cubed per kilogram, then what I have is kilopascals, kilonewton per meters squared times meters cubed per kilogram. And a Newton, if I have a Newton meter, then that's equal to a joule. Then kilonewton meter is a kilojoule. So this ends up to be kilojoules. One of those meters comes with this for the kilojoules, and then the other two meters cancel out. So you end up with the kilojoules per kilogram. So if we're using PV, make sure that your P is in kilopascals versus pascals. If you stay in kilopascals, then the PV terms always work out to be consistent with the units on the internal energy. Okay, so that's our definition of enthalpy. And similarly, we can say H is equal to an integral 0 to T of C sub P T dt. And if C is constant, C sub P is constant, then H will look like this. Now, CP is related to CV, obviously, because they're both related to energy. So, say for an ideal gas, see how this works out. If I have U is equal to C sub VT, and if I have H is equal to C sub PT, which is equal to U plus PV, then H has to be equal to C sub VT plus C sub VT plus RT, right? Because I'll end up with a PV, so which is just going to give me an RT. So what's interesting about this is that that being equal then to C sub PT, so C sub P is going to be equal to C sub V plus the ideal gas constant for ideal gases. Okay, so keep that in mind. It's an important relationship. And what we're really doing with our enthalpy, this PV term, I'd mentioned this before, is that compression energy of pushing a fluid into, say, a device. Okay, I've got a PDV term, and that becomes an important part of the amount of energy that I'm carrying with the fluid. Internal energies we typically use with a closed volume or closed mass. And enthalpy, these are typically for steady state flow through devices. Okay, so internal energy, closed system, enthalpy, open systems. So how do we get those numbers? Well, we've got the steam tables. And so the steam tables, we've got two different forms of the steam tables. One is that we have the temperature table, but there's also probably A3 or A5 will be the pressure table. And the difference between those two tables is that the temperature table lists all the temperatures in that first column. And it goes from the triple point, which is 0.01, and the internal energy, that's the 0 point. That's the datum. The enthalpy of the fluid is a little bit. Well, what is that little bit? Well, that little bit ends up to be this number here multiplied by that number there, 0.006, and it shows up as a 0.001. See, a 0.0006, and this is a 0.001 rounded up from 0.0006. So that's that little point here is that PV. I look at my change in internal energy through phase change, it is here. So this number will be equal to that number because the datum at this point is 0. Now, as I go to higher and higher temperatures, then things change. And so let's go from the triple point, and let's also look at these numbers here. That's the specific volume of the liquid. 1 over that number is the density in terms of kilograms per meter cubed. So the density of water is about 1,000. So that's 1 over that number. So the specific volume is 1 over density. And the specific volume of the gas, that is a very large specific volume because we're dealing with a very low pressure at that point. So that temperature, specific volume of the gas is really large. But as I start to put higher and higher pressure, as it's going up here, then see that volume, that specific volume of the vapor decreases dramatically, but nothing really changes with the specific volume of the liquid. There is a little bit of thermal expansion, but that's all we're seeing in this. There's really no effect of that increase in pressure. So let's go to something like 100 degrees. Okay, at 100 degrees C, the boiling point is 101,420 pascals, or 101.42 kilopascals. This is specific volume of the liquid. 1 over that number is the density, still pretty close to 1,000. Specific volume of the vapor. The internal energy of the liquid. Now we've gone from essentially 0 to 100 degrees, and the temperature is or the internal energy has increased by 419. So what is the specific heat at constant volume for water? The change in internal energy with respect to temperature. Change of internal energy is 419. Change in temperature is 100, which means the specific heat of water is about 4.19. Okay, pretty good number. So that's how you get that specific heat. There's also, we could get a value for the change in the liquid, and we're going from this point here up to that same value. But that didn't change very much. So what we find out is that for the liquid, whether we're using specific heat or specific heat at constant volume, specific heat at constant pressure, doesn't make any difference. This would be looking at the change in specific heat with respect to temperature, C sub P for the H, and it's the same as a C sub V, pretty much identical. Okay, so that's why we don't think about C sub V, C sub T, or C sub V, C sub P. We don't worry about that nomenclature if we're talking about liquids, but we do when we start talking about a vapor. Because here we go. Let's look at the vapor numbers. Here's my value of the internal energy for the vapor. So if I'm looking at the difference in the internal energy of the vapor going from this point to this point, well, it's no longer that 419. It's a number which is much less than that. The specific heat of the vapor is much less than the specific heat, or the C sub V, much less for a vapor than it is for a liquid. And you would find that if I did the same thing on my H for the gas, going from that number to this number, and it looks like I have about 175. Well, 175 over temperature difference of 100, that's 0.1 or 1.75 would be my specific heat, much less than for the liquid. Now, if I had a particular process and I came back with a condition where, say at 100 degrees at this point here, I had a specific volume that I calculated at 1. Well, what do I do with that? Well, 1 is between these 2 points here, right? It's less than that, but greater than that. And so what I would be doing is using my formula to be able to calculate it. And I don't have a V sub phase change here. So I would probably be using a relationship which is essentially from V average being equal to 1 minus X times VF plus X VG. Okay, so these two are provided, and so if I have this value of 1, then I can back out what this value of X would be. Okay, does that make sense? And the same thing would happen with any of these other properties. If I come back with an internal energy of my system that is at 1,000, well, if it's at 100 degrees, 1,000 is less than 2506, but it's greater than 419. So there'll be some quality of that. There'll be a mixture of both liquid and vapor. And the same thing happens if I'm talking about enthalpy. Okay, in enthalpy, if I have a number of 1,000, again, I'm going to be in between those 2 points, which means that I've got a quality less than 100%. Now, again, you have two sets of tables for that. One is a pressure table, and the other one is a temperature table. But if you don't find yourself in saturated conditions, or saturated means that you're called saturated temperature, which is right at the boiling point of the water, or saturated vapor, which means it's right at the condensation point of the vapor. So those saturated conditions are the two endpoints under that vapor dome. But if you're now outside of that vapor dome and you're into that superheated steam region, then it becomes a little bit more complex if you're trying to use tables. And what I haven't done in this class is use computational methods or apps or things like that to be doing that. I would imagine that there might be some good apps that get around some of the problems that you run into with the superheated steam tables. And the problem with superheated steam table is that as I go through these numbers, they're given to us at different pressures, like 0.01 megapascals, and it gives you the boiling point at that pressure right here. And this is 0.05, and this is 0.1 megapascals, which is 100 kilopascal, which is almost exactly an atmosphere. You can see the boiling point is 99.6. So each one of these pressures have a identifying it with a boiling point, and also the first line is for the conditions, the saturated conditions. For this one here, 120. Then this will go back. If you look at these tables, the pressure tables, you'll have exactly these numbers across here for the saturated vapor. We get superheated steam, which means these are all vapor. So we have superheated steam, the entropy, enthalpy, internal energy, and specific volume. So once I've identified a pressure and a temperature, then I've identified the state, and I can identify the other three properties I might be interested in: internal energy, enthalpy, and entropy. Now, what else should I say? The reason that you may consider looking, I mean, if you were doing this routinely, you would definitely want to be doing it, but sometimes we have to do what's called a double interpolation. And so if we're looking at a temperature of, say, it'd be like 125, well, we just interpolate between these two values here. But what if I gave you a number of a temperature of 275 and a pressure of 0.15 megapascals? Well, now I'm in between any of these numbers here, and I'm also in between these two pressures here. So you have to do kind of a double interpolation, and that gets pretty inconvenient and pretty difficult. I will not give you something like that on a test, but sometimes I wonder if it's better just to have some program that allows us to do that calculation.
Those are difficult when you have two different pressures. Still, the temperature is doable and stuff, but if you have something where you're going from 0.10 to 0.2 and doing those double interpolations, that gets tricky.
That's ugly, isn't it? Yeah, I mean, it shows you how to do that in the book, but it's just an instrument of torture as far as I'm concerned. And so double interpolation is something that they do to undergraduates just to teach them how to use the computer programs.
Professor, when you were talking about the X quality, the way I kind of understand it is when you're talking from the X quality from 0 to 1, you can never have an X quality greater than 1 because that is the defining moment where you're going from a mixture to a gas phase. So if you come out with something in our calculations, if we get a number like 1.5 or 1.2, we did something wrong.
You did something
Never
really
have
wrong,
anything
yeah.
greater than 1. Is that correct?
That is correct. Yeah. Yeah. And the kind of thing that you would identify if you came up with something like that and saying, oh, this isn't under the dome. Maybe this is in the superheat region. So it's those kinds of clues that, oh, I've made a little bit of a mistake here. So no, the maximum quality is 100%. The minimum is 0. And if it is cooled below that point, then it becomes compressed liquid. If it's heated above the point of 100% vapor, then what we're really talking about is superheat. So, yep, it's always 0 to 1. Can't be anything but. Okay.
And just on your internal energy, when you were talking about U and H, U being applied to closed systems and the H, the enthalpy, being applied to, was it steady flow systems?
Yes, and that's just sort of a general statement as to where we're going to be using those numbers. Of course, it's good to know the difference between, and well, in some cases, we'll be including both of those terms in looking at some situations. But in general, if I'm looking at something where I have like a turbine or a pump, something that has a steady flow through it, I'll always be looking at a change in enthalpy across that device, because I've got the pressure change, right? And that pressure change might have that flow energy associated with it.
And that's where I always found it kind of difficult or confusing is, where some applications were using internal energy like U or little u versus big H or little h. But I can see now it's correlating. So if we're using like a nozzle, a turbine, we're looking more now at enthalpy issues versus if we're looking at a heat exchanger where it's a closed system or a bottle filling application. That's where we're looking more now at internal.
Well, I think, but that's even more, that's even complex. Think of a piston cylinder.
Mm-hmm.
So the amount of mass doesn't change in it.
Right.
So if you think of it that way, that where I'm not letting the mass change, those are typically going to be represented by internal energies as the change of the heat. When I have a flow through system, I'm always looking at that flow energy, because again, that PV term that is pushing that fluid into the device and then coming out of it, that PV is pushing the fluid out of the device. And so that work energy has to be a part of this flowing system through the device. But if I just have a fixed amount of mass in there, I'm just using a C sub V. The one place where it's a little tricky is if I have a piston that sits on top of that cylinder and it keeps it at constant pressure. And in that case, it ends up just because it stays at constant pressure. And I think this is where they ended up with the C sub P terminology. So if I had heat to that where I have constant pressure, the heat that goes in is going to be related to a C sub P times the delta T. And that's because it is expanding under constant pressure. So under that one condition, that the fixed mass could be treated like a C sub P, but it could also be treated as a change of internal energy plus the work that is being done by expanding the cylinder, that PV term. They're equivalent, they're the same. Okay. And there's that one place that's a little bit confusing. If I try to use a difference in enthalpy to predict the amount of heat that goes into a piston that has a constant pressure, or into a cylinder where it's being held at a constant pressure. But in general, if it's a fixed mass, just go right to C sub V. Don't even think twice about it. Just do everything in terms of using a C sub V. If it's flowing through the system, don't even think about it. Go to an enthalpy and a C sub P. Okay? So that's superheated steam. Superheated steam, tabular values, and maybe it takes a little bit of interpolation depending on where you're ending up with temperatures and pressures. But in terms of most problems that I'm going to be giving you on tests or homework, you're going to be given pressures that are going to be specified at some given location on on your tables. And here are more values for superheated vapors. And again, we go to pretty high temperatures and pressures. And now we're going to like 8 megapascals, so that's like 80 atmospheres. We get up close to 300 degrees C. And this ends up to be kind of important because it ends up that there's this other variable that we call exergy, which is the potential of a fluid to convert its heat energy into power. And it ends up that for all different states of water, this state here, 8 megapascal, pretty close to 300 degrees, that gives you pretty much maximum amount of conversion from thermal energy into work energy comes about these conditions here. So we get to higher and higher pressures, higher and higher temperatures. That's where all those steam turbines operate. And that's because they get the highest efficiency. And so that's why we're interested in those steam temperatures at those high temperatures and pressures. And again, we're getting pretty big changes here. Each one of these ends up to be, 10 atmosphere differences in each one of these pressures. Okay, those are those values. We also have compressed liquids. And for the compressed liquids, we're looking at our values of the internal energies and the enthalpies as being very, very close. There again, it is it's kind of interesting. If I have a pressure of 5 megapascal, then the freezing point ends up being 263. What's the triple point? Well, triple point is at 0. So this is giving me a degree of subcooling that would be associated with that being under pressure. So if I could put that ice under pressure, it doesn't melt quite as easily. It's going to melt at a lower temperature. And so we're getting the different values of the internal energy. We're getting the values of the enthalpy. If I take that pressure and multiply it by that specific volume, that gives me that extra, what happens to be, six kilojoules per kilogram. And if I go to even higher pressure, what's this? I'm not understanding this value here. What the heck? Something is wrong with that. I'm not sure. That must be a superheated bale, but no, it's not. I don't know where that came from. Anyway, compressed liquid, you find them for different values of the pressure and for different temperatures. Oh, okay, never mind. Yeah, I get it. Okay, at 10 kilopascal, that's at 310. Okay, I get it. Those are that's getting close to the triple point of water. Okay, and so again, close to the triple point for each value of temperature. And again, these are all compressed. These are to that left of that vapor dome. Then I only have a liquid specific volume, and even after you get to pretty high pressures, I still see a little bit of a change. It's a PV term, and my values of entropy also listed there. And in general, we're going to be treating compressed liquids as being essentially just something that is taking heat to get it to the boiling point, or some sort of a amount of cooling below the boiling point for the liquid. Anyway, all those tables are out there. There's also, I think, some sublimation tables that you can find, giving you some information going from a liquid from a solid to a vapor phase directly. And the amount of energy for that is essentially equal to the amount of energy it takes to go from the solid phase to a liquid phase, and then the amount of energy to go from a liquid phase to the vapor phase. So the enthalpy of sublimation is larger than the enthalpy of vaporization and it's equal to the enthalpy of vaporization plus the enthalpy of solidification. So when we look at some compounds that give off more energy when they adsorb than associated with the phase change, one compound that we've been working with has been magnesium chloride as an adsorbent, road salt essentially, and ammonia. And under the right conditions, that ammonia adsorbs into that magnesium chloride, and it gives off 2.3 times more energy than it takes just to vaporize the ammonia. So it's a huge thing. I get the heat of absorption. If I get vapor to absorb into this thing, and it goes to a solid phase, gives off a huge amount of heat, and we can reverse it. So while it's happening like that, I could generate heat within that material that's absorbing that huge amount of ammonia. And if I add heat back to that salt to get to high enough temperature, it drives off that ammonia, and I can put it into a condenser, condense it, and just hold it in a tank. And so once I've driven off all that ammonia, I've got a system where I can then open up that valve and I can start pulling that vapor out of that ammonia tank. The ammonia temperature drops down to like -10, and the salt heats up to like 150. So I could do all kinds of things with that energy, anything from heating something, air conditioning, freezing, even cooking. I mean, it's pretty interesting to see how that comes about. And it does take a lot of energy for that to go from that vapor phase, that ammonia vapor, to what ends up to be essentially a solid state once it's in that ammonia. And the kind of nice thing about that is you worry a bit about transporting ammonia and what its situation would be if there's a leak in the tank. But when these batteries are completely discharged, all of that ammonia is in a solid state within that salt, and the tank is basically empty except for a little bit of vapor. Kind of a neat thing. Okay, so that's basically what we're looking at for fluids and property tables. And what we've been looking at mostly today has been the property tables for water. So I want you to go through and make sure that you get onto the homework problem, because I'll tell you right now, a couple of those homework problems are to be filling in tables to be able to figure out what the different values are, the different properties given once you've identified the state. Probably your quiz will be almost 100% on that. It's to be given a couple of different properties, and you're to find the third one. So that's the purpose behind using these tables, and it's good to get used to them and understand how to get around them, and what these different values are and how one value relates to another, what we mean by internal energy, what we mean by enthalpy, what we mean by a C sub V, and what we mean by a C sub P. And something about phase change and boiling water, and go down and maybe bake some coffee. So I hope that this was helpful for you, and I'll be editing this video, and we'll have that up on the website probably by tonight.
Professor, can you go back to ideal gas? I just want to get a quick screenshot.
Sure. Yeah, ideal gas.
Yeah, enthalpy ideal gas.
Yeah. Let's just go back to the ideal gas. That in general, all different fluids are going to behave as some sort of a equation of state. And Van der Waals equation is P plus A over the specific volume to the second power multiplied by V minus B is equal to RT. Now that looks almost familiar. In other words, if I take that P and multiply it by that V, then I have the ideal gas law, right? PV is equal to RT. This constant here was introduced by van der Waal to account for the fact that within a volume, part of that volume is the volume of the space between the molecules, but part of that volume is the volume of the molecules itself. B is meant as the volume of the molecules. And so we subtract that off, so we're giving the volume of the space. This term, I'm adding to pressure another term that has to do with something that's going to be important if I have a very small specific volume, like a liquid. So this ends up to be attractive forces. Okay, so I could have a condition where this term is very, very large to the point where P could be negative and still meet an equation of state. And you would find that in a place like in a leaf of a tree where the attractive force between the water molecule and the solid is so high that it ends up to have a negative absolute pressure for a given value of RT. So that's not an impossible state. But the van der Waal equation, it works for all kinds of different conditions, all kinds of different fluids. But for an ideal gas, where the specific volume is large, and therefore this term becomes small, or where the specific volume is large, and again, this B becomes large, then this reduces to the ideal gas. So within the ideal gas law, one thing that we are interested in terms of the internal energy and enthalpy. So our internal energy is maybe just C sub V times temperature. And we're saying that our H is equal to C sub P times temperature, right? And I should probably just ought to take this, not put that. I don't want that to be confused as a function of temperature, but it's just C sub V for constant specific heat. It just C sub P times T. Okay. So we've got these two relationships, the definition of the enthalpy and the internal energy. I also know that H is equal to the internal energy plus PV, right? So that's equal to C sub V times T. And get rid of those brackets. Okay, from this equation here, plus PV. Well, PV is RT. So that's equal to C sub V plus R times T, right? Which means from that equation that C sub V plus R has to equal C sub P for an ideal gas. And it comes from that relationship there has the whole. I can't use this relationship directly. But if I have an ideal gas, then I could go directly to this because this term here just ends up to be RT. Does that answer your question?
Yes, thank you.
All right. So how we're doing? I think we're way over time, aren't we? Way over time. So any questions on this?
Professor, I have
Okay.
a question.
Yes?
So will the lecture slides be posted by chance as well?
This lecture?
Yes, video, but also lecture slides. I saw in the files that there might have been lecture slides that we could also reference as well.
The programs I use do not create slides themselves. I mean, I suppose what I could be doing is just printing out what you're seeing here.
Oh, that's what
I
you
could do that. Yeah.
Tables, if you post them on Canvas, that would be helpful.
Yeah, those tables are definitely in the book. But you know what I can do? I could just make a PDF of this and a video.
Yeah, that's helpful. Thank you.
Okay. Any other questions?
No, thank you, Professor. You have a nice day.
All right, you too. Enjoy.
Thanks a lot, Professor. Hey,
You're welcome.
we talked about nuclear energy a little bit, and when you were mentioning about that, you know who came up to mind? And I don't know if you know off the top. Whatever happened to the Pons Flashman guys? They're at the U. Remember they made
cold fusion.
The cold fusion. I just told you now how old I am now.
Oh yeah,
I remember that
those guys.
back, was it the late 80s? They did something. Whatever happened to those guys?
No, I don't know. I didn't follow him. It was such an embarrassment for the University of Utah. By the time that happened, I was already at Berkeley, and I was just like, oh, don't, let me get into my affiliation here for just a little while. So, yeah, that was a little bit of an embarrassment. And just a second, I'm trying to rearrange this in a little bit here. Utah is, they really want to be, leading university. And I think there's a lot of pressure at the university to be doing that. So I think sometimes people jump the gun a little bit in getting information out. And there's a case of that happening. And, it's an unfortunate thing because I think that was what most people remember about the University of Utah. And I think we did have a nuclear engineering program here, and I think it kind of destroyed it. I think the reputation went.
I just remember there was a lot of backlash and a lot of scientists that were trying to duplicate and said it's not working. And one of those cases where they pulled the trigger a little too quick on that.
Well, yes, and I don't really use that as an example, but I always, for my graduate students, when they're writing papers, I say you have to put everything in that paper so that somebody can duplicate exactly what you've done. Mm-hmm. And if you don't have that detail, then it's not complete because somebody has to be able to duplicate. And that's kind of that example. You have to tell somebody exactly how you did it, and then for somebody else to do exactly the same thing for it to be valid. And if I'm the only one that did it, I'm the only one that comes up with that data, nobody else can duplicate it, then I'm wrong. That's the way science works, So that's the problem. They didn't go through and say, "Am I absolutely sure?" So that second, they thought that they were onto something so exciting. Probably their emotion got a hold of them, and then they just jumped on it too quickly and pushed it too fast.
Yeah, it just brought back that memory. I was like, "Gosh, I wonder whatever happened." And they just after that, you didn't hear much from them, and it just kind of fizzed out. At that
they did.
point.
Yeah, and like I say, we did have a nuclear engineering program at the University of Utah. It was part of mechanical engineering, and after that, just like it disappeared. Yeah. And mechanical engineering didn't even want any part of it, And I get that.
You're like, we're staying away from this.
Yeah, you know what? And I was actually one of the people that was from Berkeley. When I was at Berkeley, I was talking to my colleagues back at University of Utah, say, get rid of that nuclear reactor. That because we had just decommissioned an identical one at Berkeley, millions of dollars. Oh my word! What a pain in the butt that was. I said, look, get away from that. Get away from that as fast as you possibly can. And so University of Utah didn't, and they still have that big trigger reactor that's there in Maryland Engineering Building, and sometime that's going to have to be decommissioned. That's going to be a huge.
That's going to cost some money too to get that taken care of too. It's
could tens of millions, hundreds of millions, possibly. Yeah, it's a big deal. So that's a legacy, and so we moved it from mechanical engineering to civil engineering. So they have responsibility for it.
Give it to the civil guys.
Yeah. But I am kind of optimistic about the future of nuclear. And in fact, one of the things I'm on right now, and I'm trying to make a little bit of headway. People in Washington and people there I've been talking to, and senators, congressmen, different representatives. But what seems to be a neat way of dealing with global warming is to set a carbon tax equal to calculate about $68 a ton, because I backed that number out by looking at what is the value I get from burning carbon, and it's almost all heat. So what is the value of the heat I get from burning carbon? And it ends up to be about worth $68 a ton. of carbon dioxide that's produced. So set that as your carbon tax. Just set it at 68.
Yeah.
And it sends a really clear message. Burning carbon for heat doesn't make you money. You know, you can't make money doing that. You can burn hydrogen, you can burn nuclear fuel, you can use sunlight, you can use wind, all of those things. I'm not burning carbon. So it's all about burning carbon. Actually, two-step burning carbon and putting it in the atmosphere. So if there's a $68 a ton carbon tax, what would that change? First of all, nuclear energy would be competitive at that point. The other thing is that at $68, you'd still have coal combustion for power, but you'd also have carbon capture and sequestration. There's no way to afford it now. There's no market. Why? Why take a perfectly good coal plant and put on the extra expense of taking the energy to separate out the carbon dioxide and to blow it underground? So there is no economic advantage of doing that. But if there's a carbon tax, all of a sudden there's a big economic advantage. So I would think that if we had a carbon tax, we would not see coal power go away. We would see coal power and carbon sequestration come into play. And there'd be now carbon sequestration facilities where, as I'm bringing it out of the atmosphere, I can ship it to that facility and get paid $68 a ton to get rid of it. So there are all kinds of different things that come about from that. I think that you'd still be having coal-fired power plants, but you just have sequestration. The same thing with petroleum.
You're not getting rid of it. You're just finding a different way to dispose of it more safely or more just.
Carbon dioxide underground, put it back underground, and then in right geology, it mineralizes back. Just goes back into calcite and that kind of thing. Right? So you just mineralize it underground. So, and that technology's worked out. But, the cost is like $28 a ton to do it. You can't do it. So
the money talks. That I had a friend. He passed away now. He was now in his 80s, but he was an engineer for GM back in the 60s, and he designed the dashboards on the Buicks, on the old Buicks that he had back then. And I said, wow. And he said, wouldn't it be cool? I told him just one day, we were just talking, they have the electric cars. What have electric cars got going from a long time ago? And he said, Francisco, you don't think we had that technology back then? We could have done it, he goes, but we had the big oil guys paying all the engineers all this money to keep their mouth shut.
Exactly. Yeah. Who killed the electric car? There's a movie that was made on that back in the 70s. Who killed the electric car? GM made a bunch of them. And they proved them all out. But then they never sold them. They leased them out, and then they all pulled them back. Never to be seen again. That's cool. And now Tesla, the first company that came out and said, hey, this is the way to go, and was smart, I think, hitting the luxury market to make it a status thing to have an electric car. There's some value to that from a sales perspective. And they are incredible cars. Have you ever driven a Tesla?
I haven't. No. Just seen YouTube videos of it, and people seem to really, really enjoy it.
They're very expensive. Easily over $100,000 for a car. It's a lot of money. But they are wonderful. They're just like smooth and powerful, and wow, they're just great cars. It's I put it in perspective. I have I hate to say too much, but I've got it for a lot of reasons. I bought it really inexpensively because it had some problems, and I'm a mechanical engineer, right? So being able to fix a car and figuring out how to get that done was part of the fun of it. So I ended up buying this BMW 2011. This thing has a V8 with twin turbos in it. This thing puts out 400 horsepower, and it is a rocket. It's just an amazing car. You get into it, and it's just so smooth, and it's got just an amazing car. It's pain in the butt maintenance, but just all kinds of things that just seem to go wrong with it. But I'm doing a lot of that stuff myself. Not so big a deal. Incredible car. And I got in the Tesla, and I thought, oh my God, this drives like the best internal combustion engine car you get out there. And I put it on 400 horsepower, out of my BMW, it wouldn't keep up with that Tesla's driving. I mean, I just like that thing had, I think, a 0 to 60 time of like 2.4 seconds. And my BMW is more like 2.8. Never pushed it that hard, but it's faster, more powerful, that's smooth, and wonderful, wonderful cars. And not the maintenance problem that I have with my BMW. I just had to replace the turbos, and I had to get the oil leak fixed from the exhaust valves, and it's like that's thousands of dollars. None of those problems would have happened on an electric vehicle.
Yeah.
No. I wouldn't be leaking oil. I wouldn't be leaking refrigerant. I just it's so much better. Tires I still have to replace. The brakes you don't have to replace as often. Yeah, because
the motors.
Regenerative braking. Regenerative braking. Yeah, so
Yeah.
your brakes don't take as much wear and tear. So they're great. I'd have one in a minute if I could afford it.
It's so funny. Once I start looking more into the thermodynamics, was my background more was from an HVAC refrigeration. I used to a lot. But but I never really understood all the properties, the science behind a lot of this stuff. And so now I start looking more at thermodynamics, and it's like, gosh, thermos involves the whole world. I mean, it
does.
It applies to everything we do, not just specialized stuff, but every little day things that you do.
Yes. Oh, it does.
Dynamics. And so it's kind of helped me to develop a better appreciation for it,
Yeah, yeah. I mean, even in manufacturing, one of the things that keeps coming up, whenever you have something that is creating friction or something that is not efficient or whatever that happens to be, milling, machining, all of those things that you're dissipating energy in a non-reversible way, you've got heat. Yeah. Heat transfer problems show up everywhere because of thermodynamics. It's just thermodynamics. You put work in, if it isn't 100% efficient, you got heat. And you got a heat transfer problem you got to deal with. And so that's a part of it. And also, I was thinking, in fact, yesterday I was thinking of doing it, just going out, making a little video of just walking around with my iPhone and says, oh, here's the thermodynamic world that we live in, to be looking at ice and, because the ice was just at the right temperature, it was really slippery. And so I could say, and, here's the clouds and here's this cloud bank on top of this, these high mountain peaks, and this is what that's about. This is what's happening here. Or here's this fog that is sitting here to try to explain the world that we live in from a thermodynamic standpoint, because we are thermal beings. Oh, absolutely. And in fact, we're kind of coming to the conclusion that thermal cycling is what just gives us huge capabilities in what can be done. I mean, that's what happens in growing, right? You have to have the cycles. It's the freezing and the thawing that do amazing things that transform mountains, right? It's it's just everywhere you look. Thermodynamics is just like right at the base of it. Where do the minerals show up? If I want to be a miner, where do I look for minerals? Well, when you think about what happens, well, those minerals are in these veins because of heat, the big recirculation systems in the subsurface, because it's heated from below and cooled at the top. And so the density of all of these fluids just go up and they get lower and lower or higher and higher in density. And then they have to drop back down because they get so dense. And so you get the recirculation of all this fluid. Well, fluids are also bringing minerals with it, right?
Yeah.
Something like gold and silver, the solubility of those change with temperature. So you get the high temperature fluid that's coming up and is now coming up through these fractures and it starts to precipitate out as it gets into these colder region. And there's that vein of gold or that vein of silver or that vein of molybdenum or whatever that happens to be. And it's all just thermodynamics.
I wonder if the gold rush, those panners out there, they may have probably had the idea. They didn't understand the concept, but I bet you those people back in the days, panning for gold, knew where to look just because of those principles. They had some concept.
Yeah. And they look for other indicators, other kinds